My name is Saurabh Kadekodi. I work at Google and I'm a research scientist in the storage analytics team. And today I'm going to talk about practical design considerations for wide locally recoverable codes, or LRCs. This is work in collaboration with Shashwat Silas, Dave Clausen, and Arif Merchant at Google. Okay, so this talk is in the context of large-scale storage clusters. And as we heard in the keynote, and I completely agree with Andy Warfield that hard disks are awesome, and it's no wonder that the primary storage tier of large-scale storage clusters is made up of thousands to millions of hard disk drives. And we know that at such scales, failures are extremely common. Now, the most common way to protect against disk failures to not have data loss is to have data redundancy. It can be either in the form of replication or in the form of erasure coding. And here I've shown a 6 of 9 erasure code, which has 9 chunks in one stripe, 6 data chunks and 3 parity chunks to make a 9 chunk stripe, all striped on different disks. Now, bulk of the data today in large scale storage clusters is erasure coded. Now, the most commonly used erasure codes are Reed-Solomon codes, also known as MDS codes, the most popular MDS codes. And at exascale, systems are constantly looking at a way to lower the storage cost. And in order to reduce storage cost, there are 2 ways one can go about changing erasure codes. One is reduce the total number of parities so that you have a better ratio of data versus parity in each stripe, and therefore you can lower the storage overhead. But that may not be possible because there are constraints depending on how the data center or cluster is architected, that it might require a certain minimum number of failure tolerance. The other option is to increase K, that is increase the number of data chunks compared to the parity chunks. And note that the data chunks and parity chunks don't scale proportionally. What I mean by that is that if you take a 60 of 90 erasure coded stripe, it will have a durability that is much, much higher compared to a 6 of 9 stripe, even though the overhead is exactly the same. Okay? So wide RS codes or wide codes are codes in which you have a larger K, more number of data chunks, and a lower storage overhead. Okay? Now, wide codes reduce storage overhead, but they have a problem in terms of the reconstruction I/O. So in this wide code example, suppose one chunk fails. In order to reconstruct that, you need to read K of the alive chunks for reconstructing the failed chunk. Now, with wider and wider K, larger and larger K, this becomes I/O intensive and can be an exorbitant I/O cost. So in response to this, and actually this becomes much worse given that over 99% of the reconstructions happen due to single chunk failures. So in the response to this, the locally recoverable codes were developed and first proposed in 2012 in a paper from Azure, and they are colloquially also known as the Azure LRC code, where you partition all the data chunks into local groups, and each local group has a parity in addition to the global parities. So now if there's a single chunk failure, all you have to do is read the local group's worth of data chunks or the alive chunks in order to recover from the failed chunk in that group. So local parities mitigate the costly Reed-Solomon reconstruction, but at a higher storage overhead. So LRCs are generally optimized for handling single chunk failures. Okay? Now in today's scale, the overhead added by these local parities can also be too much given the sheer size of data. Okay? So the solution for that is wide LRCs. This is where you have taken LRC and have many local groups compared to the conventional one, many more local groups, and that makes up a wide LRC. So here, a single failure reconstruction I/O cost continues to be the same, can continue to be the same as the conventional LRC because the local group's size can still be the same. And by having more number of local groups, you can amortize the storage overhead and bring that down. So wide LRCs can provide you both lower storage overhead and a contained reconstruction I/O cost. Now, there are several factors affecting wide LRC reliability, and it's not very straightforward to deploy it in practice. The first concern is the distance of the code. Now, what do I mean by distance? So code with distance d can recover from any adversarial d-1 failures. Okay? So Reed-Solomon codes are distance optimal, meaning they have the best distance for the parameters. But LRCs might not be because they have a complicated structure involving local and global parities. Now, distance optimality or distance is generally proportional to reliability. Higher the distance, higher the reliability. But distance optimality does not mean maximum reliability. And this is a point we actually emphasize and build on in our work. Another factor affecting reliability is coefficients. So an erasure code, when it is made up, has a generator matrix which has coefficients, and that the coefficients of that generator matrix, the choice of coefficients also impacts reliability. So in LRCs, we have the maximally recoverable LRC, which have optimal coefficients, but unfortunately, currently there is no known way of constructing wide maximally recoverable LRCs in exascale friendly parameters that we are interested in to lower storage costs. And finally, you also have the layout. And by layout, I mean how the local parities are distributed and what is the coverage of the chunks of a code done by, and how the coverage is done by the local parities. And that layout also has an important role. Now, coding theorists and code designers typically focus on distance and coefficients and getting close to maximal recoverability, but they kind of ignore layout in their designs, and we show that layout also has a significant role. So the codes with same distance and coefficients but different layouts can actually have very different reliability. Now, wide LRCs, because of their width, are susceptible to multiple failures, multiple simultaneous failures in a single stripe. So in this example, I show a time series plot where the y-axis is the number of stripes, specifically the number of stripes that have at least 4 failures, simultaneous failures in them. And I compare 2 deployed wide LRC codes, one approximately 50 wide and one approximately 80 wide. And we can see that on average, the 80 wide code has many more stripes which have at least 4 failures compared to the 50 wide stripe, stressing the point that multiple failure tolerance and recoverability is an important feature of wide LRCs. So in response in this work, we designed 2 new LRCs. The first is the Uniform Cauchy LRC. So we start with an Azure LRC, basically which is built by starting with a regular Reed-Solomon code, data chunks and global parities, which are constructed using Cauchy coefficients. And I'm stressing on this because Cauchy coefficients is a conscious choice because they result in reliability very close to maximally recoverable LRCs, but layout still matters. Now, what you do is, instead of having these local groups only span data chunks, you expand all of the local groups slightly such that they also cover the parity chunks. And essentially, we want to construct equally sized local groups to form our wide LRC. Now, local parities are built by XORing either the data chunks that form the local group or the combination of data and global parities as shown in the last stripe. The intuition here is that we want to maximize the probability of spreading multiple failures that occur uniformly across the local groups, essentially make all the parities work towards the reconstruction of your missing data. This construction is very simple and is possible for a very wide selection of exascale friendly parameters, both in terms of coding efficiency and in terms of wanting to reduce storage overhead. The next kind of LRC that we design in this work is the Optimal-Cauchy LRC. Again, you start with a regular Reed-Solomon stripe and an Azure LRC layout, and then we XOR the each local parity with all the global parities in each local group. And doing that allows us to have a distance optimality proof for our Optimal-Cauchy LRCs. So Optimal-Cauchy LRCs are distance optimal. They give the best distance for the set of parameters that you choose. But again, to remind the audience, that does not mean maximum reliability. Again, this construction is very simple. you can basically start with an Reed-Solomon code, an MDS code that you're already using, and literally using pen and paper, you can build up to these either Uniform Cauchy LRCs or Optimal-Cauchy LRCs, and the constructions have been described in our paper in detail, along with the proof. So now I'm going to show different practical ways of measuring the different LRC constructions that are popular in practice. To do that, I use a 96 of 105 stripe. So this is a wide code, which has a total of 105 chunks in it, 5 global parities, 4 groups, meaning each group spans approximately 24, 25, depending on which construction you're using, and the overhead is approximately 9 point something %. So with Azure LRC, each local group is 24 chunks wide, and you have the global parities which are not protected by a local parity. In what is called the Azure LRC +1 construction, you protect the global parities by a local parity, but then divide the remaining data chunks into 3 local groups instead of 4, because you want to maintain the total number of parity and data chunks in the stripe. So each local group is 32 wide. With Optimal-Cauchy LRC, each local group is effectively 29 wide, because you XOR all the global parities in each local parity, and in the Uniform Cauchy LRCs, you have groups split up as 25, 25, 25, and 26, making up your 4 groups. So first is we look at robustness against random erasures. So a 96 of 105 LRC can recover from any 6 failures, because you have 5 global parities and 1 local parity that can allow you to reconstruct any 6 failures. Now in this experiment, we check for the recoverability from greater than or equal to 7 failures. So 7 failures, 8 failures, and 9 failures. And 9 is the maximum, because with 10 failures, you will have data loss, because there are only 9 parities in the stripe. So we run a Monte Carlo experiment with 1 million trials. Each trial involved removing 7, 8, or 9 chunks. And now in this plot, where higher is better, I showed the fraction of those trials that was recovered for 7 failures, 8 failures, and 9 failures. The crucial thing to observe here is that the Uniform Cauchy LRCs outperform the other constructions, and this is owing to their layout, because all of them are using the same coefficients in their makeup. Okay. Next is the average repair cost for 1 or 2 failures. You can think of this as the degraded mode read cost. So for the average repair cost for 1 failure, what we do is we calculate the repair cost for each chunk in the stripe and average that over the total number of chunks. And for 2 failures, we do the same, but combination of 2 chunks that are lost, which may result in a combination of local and global parities that might need to be consulted in order to reconstruct the stripe. Here, lower is better, because you want to have a lower I/O cost for reconstruction. And again, the Uniform Cauchy LRCs outperform the other LRCs on average in the degraded mode read cost. And finally, we look at the mean time to data loss, the most classic reliability metric, and we put a practical twist to it. So MTTDL usually is calculated as a Markov chain going from state 0 to state data loss. Okay? Now here in LRCs, for a 105 wide LRC, 96 of 105, until 6 failures, everything is recoverable. So there is 0 probability of data loss. But for 7, 8, and 9, now you have a probability of going to permanent data loss based on whether that stripe can be recovered or not. And these probabilities we assign based on our Monte Carlo experiment of random erasure tolerance for the different schemes that we observed. And here, higher is better. We see that the Uniform Cauchy LRCs, the other LRC constructions have relatively lower mean time to data loss compared to the Uniform Cauchy LRCs. Remember, this number is quite close. It's 0.96 compared to 1, but we are talking of MTTDL, whose value is typically in hundreds of millions of years, and so even this small percentage actually is a large number in absolute sense. Okay, and finally, what we did was we took a deployed LRC at Google and looked at the various events of stripe unavailability, including which chunks were unavailable. And then we constructed a Uniform Cauchy LRC for the same parameters. and we checked again which of those stripes could be recoverable using our mechanism compared to whatever was being used. And we saw that for recorded unavailability events, the Uniform Cauchy LRCs actually had a 33% better unavailability for these recorded events compared to the deployed LRC. So in summary, this work involved designing two LRCs which practically allow you to deploy wide LRCs without extra storage overhead using Cauchy coefficients which are very close to maximally reliable recoverable LRCs. The Uniform Cauchy LRCs improve availability by having a reduced unavailability of recorded events by up to 33%. This design is also robust to a maintenance event. So when you have when you have servers going down because of upgrades, and this kind of activity keeps on happening on a continuous basis in very large scale structures, clusters, the Uniform Cauchy LRCs and the Optimal-Cauchy LRCs allow you to deploy a code such that there is a higher chance of recovery when those events occur. Optimal-Cauchy LRCs are very simple to construct, and they're provably distance optimal. And we devise certain practical metrics for comparing the different wide LRC performances, specifically robustness to random failures, the average repair cost of 1 and 2 erasures, simultaneous erasures in a stripe, and the practical MTTDL measure. So with this, I'm open for questions, and please do visit us during the poster session.